Effects. There's no test at the end, and you don't need to know anything going in. These videos are meant for rest, for reflection, or just for the background of a quiet moment. The topics are big, but we don't tackle them. We wander through them. Sometimes with answers, sometimes with questions, always slowly. Tonight, we're asking something a little strange. Something simple on the surface, but more complicated the longer you think about it. Do black holes have a limit, or can they just keep going forever? Swallowing everything they touch? Growing and growing without end? It's a question that doesn't need an immediate answer. It's something you can just carry for a while. Let it unfold slowly, like the night outside your window. Maybe you've thought about black holes before. Maybe just in passing. Maybe you've seen an article, a simulation, a headline. They're easy to imagine as monsters. Huge, powerful, dark things that pull everything in and let nothing out. That image, a cosmic predator, is both helpful and misleading. Black holes aren't alive. They don't think, but the idea of endless consumption does something to the human mind. It stirs up fear, curiosity, awe. So let's pause. What really is a black hole? Not just an invisible void, but a region of space-time where gravity is so intense that nothing, not even light, can escape. The edge of a black hole is called the event horizon. Once something crosses it, a particle, a photon, a spacecraft, it's gone, irretrievably. It adds to the mass of the black hole. This is how they grow. They feed, but not actively. When material gets close enough, stars, gas, dust, even other black holes, it's drawn in. As it spirals inward, it heats up, glows, sometimes outshining entire galaxies. And then, silence. The light vanishes. The object is no more. So back to the question. Is there a limit? Can black holes grow without end? On paper, yes. The more mass a black hole accumulates, the stronger its gravity becomes. The larger its event horizon grows. Theoretically, if it could keep feeding forever, it could become infinitely massive. But in practice, the universe has constraints. There's only so much matter nearby. Even in galaxies, black holes eventually run out of fuel. They can become dormant, quiet, waiting. And then there's time. Black holes aren't forever. Over unimaginable timescales, they evaporate through a process called Hawking radiation. Tiny leaks of energy, shrinking them ever so slowly. For a black hole the mass of our sun, this process takes longer than the current age of the universe. Many, many trillions of years. But the point is, they have an end. So no, black holes don't grow forever. They can become vast, but not infinite. They are powerful, but not unstoppable. And that, in a strange way, makes them even more fascinating. Because in a cosmos that often feels unknowable, they offer a paradox. Something that seems eternal, but isn't. Something that hides everything, yet reveals the deepest truths about space, time, and even reality itself. So, as you drift into sleep, or just into quiet thought, hold on to that question. Not to solve it, just to feel it, just to float in it. Like starlight that almost escapes, but doesn't. The event horizon is often described as the point of no return, a cosmic boundary. It's not a wall or a solid surface, but a threshold. Cross it and escape becomes impossible. Not even light, the fastest thing in the universe, can break free. But what lies beyond it? What happens to the matter, the light, the information, as it falls inward, pulled into a darkness so complete that even time itself begins to behave strangely? This is where science becomes less certain and more imaginative. We know what happens outside the event horizon. We can measure, model, and observe the effects. But inside, we can only speculate. And that speculation opens a doorway to some of the most mind-bending ideas in physics. According to Einstein's general theory of relativity, once an object passes the event horizon, it continues to fall, not through space, but through time. Inside the black hole, all paths lead to a single point, the singularity. The singularity is the theoretical core of a black hole, a place of infinite density, a place where the known laws of physics break down. But here's the catch. Infinite doesn't mean we understand it. It actually means we don't. It's a placeholder, a red flag in the math that says, we need a better theory here. Some physicists believe the singularity doesn't even exist in the way we imagine, that our theories, pushed to their limits, are just showing us the edge of their usefulness. And so, questions arise. Does time stop at the singularity? Does matter become infinitely compressed? Or does it transform into something we can't yet describe? One radical idea is that the matter doesn't vanish or stay trapped, but instead emerges elsewhere, in a different region of space, or even a different universe. This is the basis of the white hole hypothesis, the theoretical reverse of a black hole, where matter only comes out but never goes in. It's speculative. There's no observational evidence for white holes, but the mathematics doesn't forbid them. Another possibility: what falls into a black hole is not destroyed, but stored, somehow encoded on the event horizon itself, a concept called the holographic principle. This principle suggests that all the information about what falls into a black hole isn't lost, but smeared across its surface in a kind of cosmic record, as though the three-dimensional reality we experience inside the event horizon is just a projection of that surface. It's an elegant idea, and it could help solve one of the most famous puzzles in physics: the black hole information paradox. This paradox was first brought to light by Stephen Hawking in the 1970s. He proposed that black holes emit radiation, now called Hawking radiation, and that over time they lose mass and eventually evaporate entirely. But if they evaporate, what happens to the information about what fell in? In classical physics, information can't be destroyed. But Hawking radiation, as we understand it, carries no trace of the matter's original properties. It's like burning a book and being unable to recover the story from the ashes. This troubled physicists for decades. If information is truly lost, then our understanding of physics, of determinism and quantum mechanics, needs a major revision. But if it's not lost, where does it go? Some suggest it's preserved in the quantum entanglement of particles. Others believe it's stored at the boundary of the black hole, again, that holographic surface. And some theories, wild, beautiful, and difficult, suggest that black holes are not destroyers, but bridges. Bridges to other parts of the cosmos, or even to entirely separate universes. This is the realm of wormholes, hypothetical tunnels through space-time, connecting distant points via shortcuts through higher dimensions. Could black holes be one end of a wormhole? Could the singularity, instead of being a point of destruction, be a gateway? We don't know, and we may never know, because crossing the event horizon seals the fate of whatever enters. We can't see inside. We can't send a probe and receive data back. All we have are the clues, the behavior of matter just outside, the equations of general relativity, the whispers of Hawking radiation. But even without certainty, black holes offer us something rare. They give us a place in the universe where mystery is preserved, where not knowing isn't a failure but a frontier. They are the most extreme laboratories in existence, natural crucibles for testing the boundaries of our theories. They remind us that science is not just about answers. It's about questions that remain open, that stretch our imagination, that connect physics with philosophy. Because to ask what happens beyond the event horizon is to ask about the nature of reality itself. And tonight, as we drift in thought or fade into sleep, we carry that question, not to conquer it, but to marvel at its depth. After all, some mysteries aren't meant to be solved. They're meant to be felt. When we talk about black holes, we often focus on the gravitational pull, the immense density, or the event horizon. But there's another aspect, one that's just as fascinating and perhaps more unsettling: the way black holes affect time. Time, to most of us, feels steady. We measure it in seconds, minutes, hours. It ticks by evenly, no matter what we're doing. But that's an illusion. Time is flexible. It stretches and compresses depending on gravity and motion, a consequence of Einstein's theory of relativity. And black holes? They are the ultimate time manipulators. Imagine floating far away from a black hole, watching someone fall toward it. To you, from a distance, their motion appears to slow down as they approach the event horizon. Their descent becomes sluggish. You see them fade, redshift, dim, and then stop, just hanging there at the edge, frozen in time. But from their point of view, for the person falling, time feels normal. They pass the event horizon without noticing anything unusual. They fall, and time flows forward as always. Two different experiences, both valid, both real. This isn't a trick, it's physics. This strange disconnect is due to gravitational time dilation, the phenomenon where time passes more slowly in stronger gravitational fields. Near a black hole, gravity is so extreme that time nearly halts from an outside perspective. If you could hover just outside the event horizon, minutes for you might mean centuries for the universe outside. A minute spent close to a black hole could be an eternity out there. It's a concept explored in science fiction, most notably in Interstellar, where astronauts visit a planet near a supermassive black hole and return to find decades have passed for others. But this isn't just fiction. It's based on real calculations. It's real physics. And this time, distortion doesn't just apply to human observers. It affects light. As photons climb out of a black hole's gravity well, they lose energy. Their frequency lowers. Their color shifts redder. Eventually, they become invisible, stretched out into wavelengths too long to detect. That's why black holes are black. Not because they consume light instantly, but because they trap it so deeply in their gravitational grip that it cannot return in a recognizable form. But go back to the person falling in. As they cross the event horizon, they can't see the outside universe as it was. Instead, it would seem to speed up. The entire future of the universe might flash before them in an instant. Stars aging, galaxies drifting, even the end of time itself. It's speculative, of course. No one has experienced it. No data has returned. But based on the math, based on general relativity, this is the implication. And that brings us to a haunting idea. What if someone fell into a black hole and survived? Not the singularity. We don't believe anything survives that. But what about before that, during the descent? Could they live for a time? Experience things? Observe? Surprisingly, yes, at least for supermassive black holes. You see, the tidal forces, the stretching effect of gravity, are much gentler in large black holes. In a stellar mass black hole, you'd be torn apart long before reaching the horizon. But in a black hole with millions of solar masses, the event horizon is so vast that the gravitational gradient across your body is small. You wouldn't feel a jolt, no sudden crunch. You'd fall calmly, peacefully. It's sometimes called the gentle death, not because you survive forever, but because you wouldn't notice the moment you crossed the boundary. You'd simply keep falling, with time behaving strangely around you. There's something profoundly poetic about that. The idea that the universe contains places where time becomes fluid, where direction breaks down, where future and past blur into something unknowable. And it's not just black holes that warp time. Anywhere there is gravity, there is time dilation. We've measured it on Earth, with atomic clocks on mountains ticking slightly faster than those at sea level. We correct for it in GPS satellites, which would drift if we didn't account for time bending slightly in orbit. Black holes are just the most extreme version of something that's happening all the time, all around us. They remind us that time isn't a constant drumbeat. It's a thread that curves, twists, and sometimes snaps. And if that thread can be stretched near a black hole, what does it mean for the future of time itself? Could we one day harness gravity to slow time, to preserve life, technology, even consciousness? Or are we simply passengers in time's current, flowing toward the unknown? For now, we don't have the tools to travel close to black holes. But our thoughts can. Our questions can, and in thinking about time distortion, about falling forever, we start to feel how strange and how wondrous reality truly is. So tonight, let time move slowly. Let questions stretch and echo like starlight near the edge of the abyss. Because sometimes the best journeys are the ones that happen without movement at all. Just you and time and the silent pull of something far beyond. Space is often thought of as silent, a vast vacuum, cold and empty, where no sound can travel. And in many ways that's true. There's no air, no molecules to carry the waves our ears detect. But black holes, those dense, dark enigmas, still make noise. Not noise in the traditional sense, but signals, vibrations, ripples. And in 2015, we heard them for the first time. They came from over 1 billion light-years away, a whisper in the fabric of space-time, a ripple caused by the collision of two black holes spiraling into each other, merging in a dance of gravity so powerful it shook the universe. That signal, a brief chirp detected by LIGO, confirmed a century-old prediction of Einstein's theory, the existence of gravitational waves. Let's pause on that for a moment. Two black holes, invisible, merging. And from that collision, waves traveled across the cosmos, not through matter, but through space itself. These aren't just metaphors. Gravitational waves are real distortions of space-time. When a wave passes through, it stretches and compresses the distances between objects. If you were standing still when one hit you, your height might briefly shrink by less than the width of a proton, and then bounce back. That's how subtle they are, and yet we built instruments sensitive enough to detect them. Twin detectors, miles apart, using lasers, mirrors, and vacuum tubes to measure distortions smaller than an atom. That detection changed everything. It wasn't just proof of Einstein's theory. It was the birth of a new way of observing the universe. Before this, astronomy was mostly visual. We looked at light, visible, infrared, X-rays, gamma rays. But light has limits. It can be blocked, absorbed, distorted. Gravitational waves? They pass through everything. They carry messages from the darkest corners of space, from places light can't escape. With them, we can now hear the universe in a whole new way. And what a sound it is! The merger of black holes is like the crashing of cymbals in a cosmic orchestra, brief, sharp, but powerful enough to ripple through space-time for billions of years. Each detection tells a story of stars long dead, of masses beyond comprehension, of motions that shake the universe. Since 2015, we've detected dozens of black hole mergers, each one slightly different. Some involve equal-mass black holes. Others are mismatched. Some spin. Some don't. But each time the signal carries information about their mass, their speed, their final moments before becoming one. And sometimes the merger creates something unexpected, a recoil. The newly formed black hole can be kicked through space, like a stone skipping across water, if the collision is uneven. Imagine that, a black hole traveling through space at millions of kilometers per hour, propelled by nothing but its own creation. These are not just curiosities, they're clues. Each wave helps refine our models. Each signal brings us closer to understanding how black holes form, grow, and move. And there's more. Sometimes black hole collisions are accompanied by flashes of light, if there's gas around. When two black holes spiral together in a cloud of matter, the gas can heat up, shine, scream into the void just before being swallowed. This gives us two views of the same event, one in light, one in gravity. A cosmic duet. And soon, we'll be able to hear more than just black holes. Neutron stars, dense remnants of exploded stars, also collide. Their mergers create gravitational waves too, and also produce elements like gold and platinum. You might be wearing atoms forged in one of those ancient collisions, carried from a neutron star merger billions of years ago, across time, into your bloodstream, your jewelry, your memories. Black holes, in their silence, helped us hear that story. And that's the paradox. They emit no light. They swallow sound. But through their gravity, they speak volumes. They are drummers in the cosmic band, silent, invisible, but setting the beat that shakes the stars. And perhaps what's most humbling is this: we didn't even know we could listen. Gravitational wave astronomy is barely a decade old, but it's already rewriting our understanding of the universe. And it's just beginning. In the years to come, more detectors will join the network. They'll be placed in Europe, Japan, even space. Satellites listening to the farthest corners of the cosmos. Together, they'll create a gravitational ear around Earth, allowing us to triangulate, to pinpoint, to watch, or rather, to listen, as the universe unfolds. We might one day detect the merging of supermassive black holes, the titans at galactic centers, or hear the rumble of primordial black holes, if they exist, formed moments after the Big Bang. We may even uncover something stranger, because every new way of observing has led to surprises. Radio waves showed us pulsars, X-rays revealed black hole candidates, and now gravitational waves are pulling back another curtain. All thanks to the soundless symphony of black holes. So tonight, as you rest, imagine space not as empty and silent, but alive with rhythm. A universe humming softly in frequencies we've only just begun to hear. A music older than light, played by giants no eye can see, and heard, finally, by minds ready to listen. When we think of black holes, we often picture them as the remnants of collapsed stars or the giants lurking at the centers of galaxies. Massive, ancient, born in the aftermath of violent explosions or the steady swallowing of cosmic matter. But what if some black holes are older than stars? What if they were born not from death, but from birth? Welcome to one of the most intriguing possibilities in modern cosmology: primordial black holes. These black holes, if they exist, would have formed in the very earliest moments of the universe, within the first second after the Big Bang. Not from collapsing stars, but from intense fluctuations in density. Regions where matter piled up just enough to collapse under its own gravity, even before atoms or light had time to form. They are, in theory, relics from a time before time as we know it. Let's imagine it. A universe just born, not yet a minute old. Temperature, billions of degrees. Pressure, unimaginable. Matter and energy rushing outward in every direction, chaotic and hot. But not perfectly smooth. Tiny quantum fluctuations, the seeds of galaxies to come, rippled through the early universe. In some spots, these fluctuations were so dense, so compact, that they collapsed into black holes on the spot. These are the primordial black holes. Unlike their stellar cousins, they could have come in any size, from microscopic to millions of solar masses. Their mass spectrum could be wide, varied, and full of surprises. Some might have evaporated quickly via Hawking radiation. Others might still be drifting through space today, invisible, ancient, undetected. And here's where things get even more fascinating. Some scientists speculate that primordial black holes could be a component of dark matter, the invisible substance that makes up about 27% of the universe. We don't know what dark matter is. We've never seen it directly. But we've mapped its effects. It holds galaxies together. It shapes cosmic structure. And primordial black holes, if they exist in the right numbers and sizes, could explain some of those effects. Could the dark scaffolding of the cosmos be built on ancient black holes? It's a bold idea, and it's still debated. But recent observations have reignited interest. In 2019, the LIGO and Virgo detectors observed several black hole mergers with strange characteristics. Black holes heavier than expected, and more common than predicted by stellar evolution models. Could these be primordial? Maybe. It's too early to say. But the pattern is curious, and the possibility that we are hearing the death cries of black holes older than galaxies is breathtaking. Primordial black holes also offer potential answers to other mysteries, like the supermassive black holes we see at the centers of galaxies. Some of them formed so early in the universe's history, it's hard to explain how they grew so big, so fast. But what if they didn't grow? What if they started that way? A primordial black hole, born with 1 million solar masses, could act as a seed, drawing in matter, forming stars and galaxies around it, rather than the other way around. In this view, black holes didn't just emerge from galaxies. Galaxies emerged from black holes. It's a reversal, a reimagining. And while it's still theoretical, new telescopes, like the James Webb Space Telescope, are pushing further into the early universe, looking for the light of the first galaxies, the first stars, and perhaps the gravitational shadows of something even older. Primordial black holes might also leave behind signatures in the cosmic microwave background, the afterglow of the Big Bang, tiny distortions, lensing effects, anomalies in the smoothness of that ancient light. We're searching, we're listening, because if we could find even one confirmed primordial black hole, it would change everything. It would give us a glimpse into the first second of the universe, a time we can barely model, let alone understand. It would be like finding a fossil from before the Earth cooled, a message in gravity from a time before time. And yet, in some ways, these black holes may be closer than we think. They could be drifting through our galaxy right now, passing through solar systems, maybe even through our own solar system. Silent, dark, undetected, not dangerous unless we happen to be in their direct path, but present, real, ancient passengers in the sea of stars. They challenge our assumptions that all black holes are born from stars, that galaxies came first, that darkness follows light, because perhaps in the beginning there was darkness, and from that darkness everything else emerged. Primordial black holes remind us that the universe still holds secrets it has never revealed, that not everything bright is important, and that sometimes the oldest things leave no light at all, only gravity, silence, and mystery. Tonight, let that mystery wrap around you like the night sky. Imagine a black hole older than time, drifting, waiting, whispering. And remember, in every direction you look, there may be something out there, older than light, still pulling on the fabric of reality, waiting to be found. There's a theory, strange, elegant, and deeply unsettling, that suggests everything you've ever seen, touched, loved, or feared might be a projection. Not an illusion, not fake, but a hologram, a three-dimensional reality encoded on a two-dimensional surface. It's called the holographic principle, and it begins, as so many great mysteries do, with black holes. Let's return to the edge of a black hole, the event horizon. We know that anything crossing this invisible boundary is gone, irretrievably lost to the outside universe. Or so we thought. But in the 1970s, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, and slowly evaporate over time. If they eventually disappear, what happens to the information they swallowed? In physics, information is sacred. It can't simply vanish. Even if an object is destroyed, the information about its original state must somehow remain. But black holes seem to erase it permanently. This contradiction became one of the most profound puzzles in physics, the black hole information paradox. To solve it, physicists began to wonder, what if the information isn't lost inside the black hole, but stored on its surface? That's where the holographic principle comes in. It suggests that everything happening inside a black hole, all the matter, energy, time, and information, is encoded on the event horizon like a cosmic film strip. The three-dimensional experience inside is just a projection of that two-dimensional information. But if that's true for black holes, could it be true for the entire universe? Could our entire 3D reality, from stars and galaxies to forests and cities to your thoughts and dreams, be encoded on a vast two-dimensional surface at the boundary of the cosmos? This idea isn't science fiction. It's a serious theory, born from the crossroads of quantum mechanics and general relativity. In 1997, physicist Juan Maldacena proposed a version of this principle in string theory, showing that a certain kind of universe with gravity could be mathematically equivalent to a universe without gravity on its boundary. In other words, a 3D universe could emerge from a 2D one. Think about that. You are living in 3 dimensions. You move forward and back, up and down, left and right. But beneath that experience, underneath the math, everything might be described by a flat sheet of information. Just as a hologram on a credit card contains a 3D image encoded in 2D light patterns, so too might our universe arise from a flat horizon we can't even perceive. It's not just theory, there are hints. When scientists study black holes, the amount of information they can hold doesn't depend on their volume. It depends on their surface area. That's not what we'd expect. In most systems, more space means more information. But not here. Black holes flip that logic. They store information on the edge, not inside. And if black holes obey this rule, maybe the universe does too. Some physicists believe this principle could solve the tension between quantum mechanics, the physics of the very small, and general relativity, the physics of the very large. Because at their core, both theories work beautifully, but they don't agree. They offer different pictures of reality. The holographic principle might be the bridge between them. It's speculative, yes, it's unproven, but it opens doors. What we call space may be emergent, a phenomenon that arises from more fundamental ingredients, like temperature emerges from molecular motion. Space may not be basic. It may be built. And if space is emergent, maybe time is too. Maybe time, memory, even causality, the idea that one thing leads to another, are part of a deeper structure we've only just glimpsed. So what does it mean? If our universe is a hologram, does it make our lives less real, less meaningful? Not at all. Think of a rainbow. It's made of light, of refraction and angles. It's not solid, but no one would say it isn't beautiful. Reality in any form is still real, whether it's built from particles or pixels or projections, whether we're in a fundamental universe or a holographic one. The experiences we have, love, wonder, fear, curiosity, are genuine. And perhaps the holographic principle doesn't make us smaller. Perhaps it makes us part of something grander, something more intricate and mysterious than we've ever imagined. Because if reality is written on the edge of the universe, then we are written on the edge of time. And every thought you've ever had, every story told, every dream dreamed, it's part of that script, etched into the fabric of existence, preserved, projected, alive. So tonight, when you close your eyes, imagine the stars around you as characters in a story written across the sky. Imagine yourself as light dancing between dimensions, a ripple of something deeper, a shadow of something greater. Not less real, but more connected, more eternal, more cosmic than ever before. Have you ever felt like reality was just a little off? That the world seemed too structured, too ordered, or maybe too chaotic in strangely consistent ways? What if there's a reason for that? What if this universe, the stars, the galaxies, your memories, your body, is not the fundamental reality, but a simulation? It sounds like science fiction, like something from The Matrix, or a thought experiment dreamt up in a philosophy class. But it's a hypothesis that real scientists, philosophers, and even tech pioneers are now seriously considering. The simulation hypothesis. At its core, the idea is simple. If it's possible to simulate a universe with conscious beings in it, and if a civilization ever becomes advanced enough to do so, then statistically, it's more likely we are living in a simulation than in base reality. Here's the logic. In our own lifetimes, we've gone from Pong to photorealistic open-world video games, from analog static to virtual reality, so immersive it can fool our senses. Now, imagine what might be possible in 1,000 years, or 100,000. If a future civilization can simulate not just weather systems or entire cities, but conscious minds, then what's to stop them from creating entire universes? They might do it for science, for curiosity, or maybe for reasons we can't even begin to imagine. And if they create millions, even billions, of such simulated worlds, then ours could be one of them. In fact, according to philosopher Nick Bostrom, unless civilizations universally stop advancing or choose never to simulate reality, then it's overwhelmingly likely we're in a simulation. The math is terrifyingly elegant, but how would we know? What signs would a simulation leave behind? Some scientists point to the pixelation of reality, not in visuals, but in fundamental units. Space and time, it turns out, may not be continuous. At the smallest scales, they behave like discrete chunks, like pixels in a cosmic image. This is called the Planck scale, the smallest possible length and time measurable in the universe. Below this scale, space and time might not even exist in any meaningful way. That's strange. That's digital. Others suggest we could find glitches, inconsistencies in physical constants, or mathematical patterns that shouldn't occur naturally. And some even believe that quantum phenomena, like particles being in multiple states until observed, could be signs of a simulated rendering system. That reality only renders what is being looked at. Just like a video game doesn't render every blade of grass until you walk through the field. Maybe the universe does the same. Now, to be clear, this is all speculative. We don't have proof, but we also don't have disproof, and that's what makes it unsettling. If we are in a simulation, what's outside of it? Who or what is running it? And why? Some imagine vast superintelligences. Others think it's future humans studying their past. Some even believe it could be a form of cosmic evolution, that simulations birth new universes with their own laws of physics, forming a branching tree of realities. But perhaps the most profound question is this: would it change anything if we knew? If you found out tomorrow that this life, this planet, this universe was simulated, would your love be less real? Would the sky be less beautiful? Would your memories feel like code instead of meaning? Maybe not, because experience is still experience. Whether it comes from atoms or algorithms, what you feel is real to you. and perhaps that's enough. In fact, the simulation hypothesis can be oddly comforting. If our universe is coded, then it has structure. If it has structure, maybe it has purpose. Maybe someone, or something, is watching, caring, updating the system. Maybe the universe isn't silent, but waiting. And if we are inside a simulation, maybe we can communicate up, ask questions of the beyond, like ancient humans praying to stars they didn't understand. We don't need to believe in a simulation to ask deeper questions about reality. That's the point. Whether the world is physical, holographic, or simulated, the mystery remains. What is consciousness? What is reality? And who or what is asking? Maybe the reason the simulation hypothesis fascinates us is because it forces us to confront those questions. And maybe, just maybe, it inspires us to live more consciously, to write better code in our own minds, to create meaning regardless of origin. Because even if this is a simulation, the story is still ours. We are the characters, the plot, the spark. So tonight, look around, at the sky, the trees, your hands. Ask yourself, what would I do if I knew this was all a simulation? And then, do it anyway. Because whether reality is rendered or real, it's the only one we've got, and that makes it precious. We often speak about the universe as if it were a place, something with edges and a center, a vast sphere expanding into something. But what if there is no edge? Or worse, what if there is, and we simply can't reach it? Tonight, let's drift to the farthest edge of imagination and ask, what lies beyond the observable universe? First, we need to define our terms. When we say universe, we usually mean the observable universe, everything we can see or detect, limited by the speed of light and the age of the cosmos. Because light takes time to travel, we can only see objects whose light has had time to reach us since the Big Bang, about 13.8 billion years ago. But due to cosmic expansion, the actual size of the observable universe is much larger, around 93 billion light-years across. Beyond that, we don't know. It's not that there's nothing. It's that the light from those places hasn't reached us yet. They exist, or at least they did, but they're beyond our cosmic horizon. Imagine standing on a beach at night. You see the waves, the stars above, but you can't see over the ocean's curve. That doesn't mean the world ends there. It just means your sight does. That's the limit of the observable universe. So what's outside of that? There are several possibilities. 1. More universe. More galaxies, stars, planets, just like the part we can see, stretching on forever. The same physical laws, the same cosmic background, just more. This is the simplest idea, and it's supported by what we observe. The universe looks remarkably uniform in all directions. No matter where we point our telescopes, things look similar. That suggests the universe might be infinite, or at least much larger than we can ever observe. But even in an infinite universe, you hit paradoxes. If space goes on forever, does that mean everything that could possibly exist must exist? Every arrangement of atoms, every version of you, every possible history, repeating again and again in endless combinations. Some physicists say yes. This is the idea of the cosmic multiverse, not just many worlds, but infinite space with infinite variations, playing out every possibility. But other theories suggest something stranger. That space isn't infinite, that the universe has a shape. It might be curved, like the surface of a sphere, but in higher dimensions. In this model, if you could travel in one direction long enough, you'd eventually loop back around to where you started, like flying around a planet, except in cosmic 3D. And then there are theories that suggest our universe is just one bubble in a much larger cosmic foam. According to some versions of inflation theory, the rapid expansion that occurred moments after the Big Bang could have created not just one universe, but countless others, each forming in its own bubble with its own physical laws. In this picture, our universe is not the whole, just a drop in a vast sea of disconnected realities. A multiverse not in space, but in possibility. And beyond the edge of our bubble, a churning chaos, a quantum field frothing with potential, birthing universes with every fluctuation. Some hot, some cold, some with gravity, some without, some where time runs backward, some where stars never form, some where nothing ever changes. But here's the most haunting truth. We might never know, because the speed of light is finite, because space is expanding, faster than light can travel, because the farther we look, the faster things recede. And eventually, beyond a certain point, we lose them forever. Galaxies pass beyond our cosmic event horizon. They don't disappear, but their light will never reach us again. And with each second, the observable universe shrinks, not in size, but in content. The universe continues to expand, but the parts accessible to us grow ever smaller. Eventually, if cosmic acceleration continues, we'll be alone, a small island of light in an ocean of dark, the rest of the universe receding beyond reach, beyond memory. It's poetic and terrifying, but also profoundly humbling. Because even if we never reach the edge, even if we never see what's beyond, we know enough to ask the question, and that, in itself, is extraordinary. So what lies beyond the edge? Maybe more stars, maybe other universes, maybe nothing we can ever imagine, or maybe, just maybe, a mirror, a boundary, a frame, a place where the simulation ends, or where a deeper truth begins. We don't know, but we're reaching, we're listening, and even in the silence we find meaning. Because to ask what lies beyond is to admit that we don't have all the answers, that we are explorers, not just of space, but of ignorance. And in the dark, at the edge of all we can see, a question floats. What if? Tonight, let that question be your companion. Let it guide your thoughts beyond galaxies and toward the unknown. Because beyond the edge of the universe may lie the edge of understanding, and just maybe, the beginning of something greater. The stars above feel eternal. Galaxies hang in the darkness like frozen fire. The night sky gives the illusion of stillness, a universe at peace. But that calm is a lie. The universe is not standing still. It's flying apart, faster and faster with every second. And the reason why is something we barely understand. It's called dark energy. It doesn't glow. It doesn't clump into stars or planets. It doesn't even seem to interact with matter in any conventional way. But it makes up more than 2/3 of the entire universe. We discovered dark energy not through sight, but through silence. In the late 1990s, astronomers studying distant Type Ia supernovae, massive stellar explosions used as cosmic mile markers, found something shocking. These explosions were dimmer than expected, which meant they were farther away than expected, which meant the expansion of the universe wasn't slowing down due to gravity, as everyone assumed. It was speeding up, accelerating. Some unknown force, was pushing the universe apart, not just stretching space, tearing it open. We named it dark energy, but naming it didn't mean we understood it. In fact, we still don't. It could be an inherent property of space itself, something Einstein once called the cosmological constant. According to this idea, empty space isn't truly empty. It has energy, and that energy exerts a repulsive force. The more space expands, the more space there is to generate repulsion. And so the cycle continues. Faster, farther, forever. But there are other theories. Some suggest dark energy is a dynamic field, changing over time, not constant but evolving. Others believe it might be a symptom of higher dimensions, leaking into ours from beyond the fabric of space-time. And some wonder if dark energy even exists at all. Maybe our understanding of gravity itself is flawed at cosmic scales. Maybe we need a new theory, one that rewrites what we think we know. But whatever dark energy is, or isn't, we see its effects. Galaxies are drifting apart. Space is expanding, and the expansion is accelerating. So what does that mean for the future? It depends. In one scenario, known as the Big Freeze, the universe continues expanding forever. Galaxies become too distant to see. Stars burn out. Black holes evaporate. The cosmos cools into darkness, a slow fade into nothing. In another, more violent ending, called the Big Rip, dark energy increases over time. Eventually, its repulsion overcomes every force, pulling galaxies apart, then stars, then planets, then molecules, then atoms, until nothing remains. Even space-time itself unravels, and the universe ends, not with a bang or a whimper, but with a shred. A third possibility? That dark energy reverses, collapses, triggering a big crunch, where the universe contracts back into a singularity, or perhaps oscillates in an eternal cycle of expansion and collapse, the Big Bounce. We don't know which fate awaits us, because we don't know what dark energy truly is. We only know it's powerful, and that it is everywhere, even here, in the space between atoms, in the emptiness around Earth, in the darkness behind the stars. You are surrounded by it, right now, and yet you'll never touch it, never see it, only feel its consequences across billions of light years in the shape of the cosmos itself. There's something poetic about that, a force so vast, so dominant, and so invisible. It reminds us how little we truly know, that the universe is not made only of matter and light, but of mystery, and that in the silence between galaxies, there is a song we cannot yet hear, but we know it's playing. Dark energy is a reminder that the universe is not finished. It is still writing itself, with invisible ink, still expanding, still unfolding, still becoming. And so are we. As you drift into sleep tonight, imagine the galaxies racing apart, carried on the current of something vast and unseen. And ask yourself, what fills the void? What holds it all together? What pushes it all apart? And could there be a force stronger still, not to destroy, but to understand? The universe is expanding, and maybe, just maybe, so is our capacity to wonder. We wake to it. We measure it. We race against it. Time, the silent backdrop to every moment of our lives. But what is it? A flowing river? An arrow pointing forward? Or something far stranger? Tonight, let's slow everything down and ask a question most never dare to truly confront. What is time, really? At first glance, time feels simple. It ticks. It flows. It divides events into before and after. But in physics, time is not so obedient. In Einstein's theory of relativity, time is not absolute. It stretches, it bends, it dances with space. Together, they form a unified fabric, space-time. And in this fabric, movement affects time. The faster you move, the slower time passes for you, relative to someone at rest. This is not science fiction. It's been tested, confirmed. Astronauts on the International Space Station, moving at thousands of kilometers per hour, age slightly less than people on Earth. Atomic clocks flown on planes tick differently than those on the ground. Time, it seems, is elastic. But there's more. Gravity also affects time. Near massive objects, like planets or black holes, time runs slower than in empty space. Clocks on satellites orbiting Earth must be adjusted because they experience less gravity, and thus, time moves faster for them than for us on the surface. It's called gravitational time dilation. So already our intuition is failing. Time isn't fixed. It's not universal. It's relative, not just philosophically, but physically. But this raises a deeper question. If time flows differently depending on where you are, is it even flowing at all? Or is that an illusion? Some physicists suggest that time doesn't pass, that all moments in time exist simultaneously, like pages in a book. We experience time sequentially, but that might just be the way our brains interpret reality. To the universe, there may be no past or future, only a vast, four-dimensional block of space-time where every event already is. This is called the block universe theory. In this view, your birth, your death, every breath in between, all coexist in a timeless structure. It's unsettling, but also strangely beautiful, because it means nothing is truly lost. Every moment is etched into the fabric of reality, forever. But then, why do we feel time pass? Why do we remember the past, but not the future? Why does entropy, the measure of disorder, always increase? That's the real mystery. Time has a direction, a flow from order to chaos, from low entropy to high. Eggs crack, but don't uncrack. Ice melts, but never spontaneously refreezes. This is the arrow of time. But here's the twist. The fundamental laws of physics are time-symmetric. They work just as well forward as backward. Nothing in the math demands time move in one direction. The arrow of time seems to come not from physics, but from initial conditions. The fact that the universe began in a state of incredibly low entropy, and ever since, it's been unraveling. But that might not be a cosmic law, just a cosmic accident. In some theories, time could flow backward in other regions of the universe, or in other universes entirely. And what about quantum mechanics? In the realm of the very small, time behaves strangely. Particles don't have definite states until observed. They exist in superpositions, smeared across possibilities, and some interpretations suggest time itself may emerge from entanglement, the mysterious connection between particles across space. In this view, time is not fundamental. It's not a backdrop. It's a construct, emerging from the relationships between things. And perhaps it's an illusion altogether. This is the radical view of physicist Julian Barbour, who suggests that time doesn't exist, that all we have are nows, individual, complete configurations of the universe. No flow, no passage, just a cosmic slideshow, each frame perfectly still, but our minds give it motion. If that's true, what then is memory? What is choice? What is change? Are we just patterns skipping across frozen frames? Or is our perception of time the most real thing of all? Maybe we can never answer these questions. Maybe time hides behind the veil of consciousness, so close, so intimate, that we can't step outside it to see what it truly is. But perhaps we don't need to. Perhaps it's enough to know that time is not what it seems, that it bends, shifts, expands and contracts, that it might not flow. And yet, here we are, living in it, measuring it in seconds, feeling it in heartbeats, losing it in dreams. So tonight, let time dissolve. Let it slow, stretch, and shimmer. Let go of clocks, of calendars, of deadlines, and ask yourself, if time is an illusion, what becomes possible when we stop believing in it? Maybe the future is already here. Maybe the past never left. Maybe this moment, right now, is all there ever was, and all there ever will be. And that's enough. You're listening, you're thinking, you're aware. But stop for a moment and ask, who is aware? What exactly is this quiet voice inside your head? What is consciousness? This isn't just a philosophical musing whispered in candlelit rooms. It's one of the greatest scientific mysteries. Perhaps the greatest. Because everything we experience, every color, sound, memory, hope, and fear, exists inside it. And yet, we have no idea how it works. Consciousness is what allows you to perceive the world, reflect on your own existence, and ask, what is consciousness? It's not simply reacting to the world. Machines can do that. It's being aware that you're reacting. Self-awareness, inner experience, subjectivity. The ancient Greeks called it the soul. René Descartes called it the thinking thing. Buddhists speak of it as a stream with no true beginning or end. But modern science, still groping in the dark. Let's start with what we do know. The brain, roughly 1.4 kilograms of neurons, blood, and chemical soup, somehow gives rise to the mind. Billions of neurons firing in patterns, electrochemical signals dancing across networks, synapses exchanging microscopic sparks, and from that emerges a sunset, a song, a sorrow. But how? This is known as the hard problem of consciousness, a term coined by philosopher David Chalmers. It's not hard because we can't trace brain activity. We can. We can measure which regions of the brain light up when you see red, feel pain, or recognize a face. But none of that explains why those experiences feel like something. Why red feels warm. Why pain hurts. Why love can move you to tears. Why anything is experienced from the inside. That's the hard problem, and no theory fully explains it. Some neuroscientists suggest consciousness is an emergent phenomenon, something that arises when systems become complex enough, like weather emerging from air and temperature. Others say it's all an illusion, that what we call consciousness is just an echo of brain activity, a story the brain tells itself. But if consciousness is an illusion, then who is being fooled? Even the illusion must be experienced by something. So the mystery remains. Other researchers propose bold ideas, like integrated information theory, which suggests that consciousness arises wherever information is processed in a deeply interconnected way. Under this theory, any system, biological or artificial, could be conscious if it has enough integration. That raises eerie possibilities. Could AI become conscious? Could the internet already be? Could consciousness be everywhere? This idea, known as panpsychism, suggests that consciousness is a fundamental property of the universe, like mass or charge. That even atoms may have primitive awareness, not thoughts, not feelings, but the seed of experience. If that's true, then consciousness didn't emerge. It was always here, from the first particle, the first photon. The universe itself may be conscious, or at least capable of it. And in you, in me, in every sentient being, the universe awakens to itself. Think about that. You are not separate from the cosmos. You are the cosmos, folding in on itself, to observe, to reflect, to wonder. In this view, the stars aren't just out there. They're in here too. The atoms in your body were forged in ancient stars. Your thoughts are shaped by evolution, culture, memory, and sensation, but also by laws that govern light, gravity, and time. You are the universe looking inward, a self-reflective echo in the long silence of space. And yet, we still don't know how it happens. Why does a brain give rise to a self? Why do some arrangements of matter feel like someone is home? Is there a threshold, a switch, a secret structure we've yet to find? Or is it all an illusion spun by neurons and necessity? We may never know, but the search itself is sacred, because it pushes us to redefine what it means to be alive, aware, real. Could consciousness survive beyond the brain? Could it be transferred, uploaded, shared? Could it one day be detected in machines or in forms of life we can't yet imagine? And what if it's bigger than us? What if galaxies have minds? What if black holes dream? What if the universe thinks? These aren't just fantasies. They are reflections of our deepest yearning to understand ourselves, not as bodies in space, but as selves in reality. And here's the most beautiful truth. Even if we never answer the question is still worth asking. Because to ask, what is consciousness, is to be conscious. It's the echo of awareness calling itself by name, and that, in itself, may be the answer. So tonight, let your thoughts drift. Not just through stars or time, but through your own mind. Feel the awareness behind the thoughts, the silence behind the words, the stillness behind the breath, because in that silence, you are. Everything that has a beginning must have an end. We live our lives beneath the stars, wrapped in the illusion of permanence. The sky appears unchanging, the cosmos eternal, but it isn't. Just as stars are born and die, so too may the universe itself be mortal. And tonight, we ask the most haunting of questions. How does everything end? The universe began with the Big Bang, an explosion not of matter in space, but of space itself. Time, energy, dimensions, all born in a single breath. For billions of years, galaxies have been moving away from each other, carried by the stretching fabric of space-time. And that expansion, driven now by dark energy, is accelerating. So what does that mean for the far future? Scientists have proposed several endings. Let's begin with the quietest, and perhaps the most chilling. 1. The Big Freeze. If dark energy continues to push space apart, galaxies will drift farther and farther away. Over trillions of years, star formation will cease. The last stars will burn out. The skies will go dark. Black holes will remain, slowly evaporating via Hawking radiation, until even they disappear. What's left? A thin, cold sea of particles. Space-time stretched thin. No structure, no energy gradients, no memory of stars, life, or meaning. Just silence. This is the heat death of the universe, not because it's hot, but because entropy has reached its maximum. There's no more change, no more information, only stillness. It's not dramatic, but it's total. 2. The Big Rip. In another scenario, dark energy doesn't stay constant. It grows stronger. So strong, in fact, that it begins to tear apart gravity itself. First, galaxies unravel, then star systems, then planets, then molecules, then atoms. Eventually, even space-time rips. This is the Big Rip, the most violent end imaginable. The fabric of reality torn asunder. No warning, no survival, only dissolution. But it depends on the nature of dark energy. And so far, we don't know if it will behave this way. Still, it's possible. 3. The Big Crunch. Now imagine a reversal. If dark energy weakens over time, gravity might reclaim its dominance. Galaxies would slow, stop, and then begin to fall inward. The universe would collapse. Faster and faster, hotter and denser, until everything returns to a single point. A mirror of the Big Bang. This is the Big Crunch, and some theories suggest it might lead to a big bounce, where the universe is reborn in another expansion, cycling endlessly through creation and collapse. A cosmic heartbeat. But evidence for this is slim. So far, expansion shows no sign of slowing. 4. Vacuum decay. And then, there's the strangest possibility of all, that we live in a false vacuum. In quantum field theory, the vacuum isn't empty. It has energy. And our universe may not be in its most stable configuration. It might be in a metastable state, temporarily stable, but vulnerable. If that's true, a bubble of true vacuum could form somewhere. a more stable state of reality. And it would expand at the speed of light, destroying everything in its path. Laws of physics would change. Matter would dissolve. Chemistry would stop working. We wouldn't see it coming. No pain, just nothing. It sounds terrifying, but also strangely peaceful. A cosmic reset, a new kind of universe born from the old. Maybe one with different particles, different dimensions, different rules. Maybe one without consciousness, or maybe one with more. But here's the secret. The end doesn't erase the beginning. We fear the end because we value what we've built, what we've known, what we are. But the fact that the universe may end, that it must end, doesn't make it less beautiful. It makes it more. Because meaning isn't found in eternity. It's found in the fleeting, in the brilliance of stars that know they will die, in the minds that ask these questions, in the love that arises in a temporary world. If the universe ends, if all light fades, it will have burned bright. It will have sung its song, and in a small forgotten corner of that grand symphony, you existed, you thought, you loved, you wondered, and maybe that's the only immortality that matters. So tonight, look at the stars not as eternal beacons, but as moments, brief, glorious, and precious. Let the future be unknown. Let the silence come someday, because in this moment, the universe is alive, and so are you. The universe feels infinite. Its stars, endless. Its time, eternal. Its rules, absolute. But what if they aren't? What if there's a way, however distant, however theoretical, to leave the universe itself? Tonight on Infinity Beyond, we explore a question that borders on the impossible. Can we escape the universe? To begin, we must ask, what is the universe? It's not just the stars and galaxies we see. It includes space, time, energy, matter, laws of physics, everything we can observe, touch, or imagine. It's the sum of all physical existence. To leave it would mean stepping outside space, beyond time, past the framework that defines reality itself. It sounds absurd, but so did flight once. So did walking on the moon. So let's ask, what would escaping the universe even look like? And could it ever be more than a dream? 1. The multiverse route. Some theories in modern physics suggest that our universe is not alone. Instead, it may be part of a multiverse, an immense collection of bubble-like universes, each with its own laws of physics. In this view, our universe is one bubble floating in a cosmic foam. Other bubbles might form and vanish. Some may be lifeless. Some might be wildly different, with alternate dimensions, reversed time, or physical laws we can't imagine. Could we travel from one bubble to another? Theoretically, yeah, through a structure known as a wormhole. A wormhole is a hypothetical tunnel through space-time, connecting distant points or even different universes. If such a thing could be stabilized, it might serve as a cosmic doorway. But wormholes, if they exist, are unstable. They collapse almost instantly. And we don't know if they can connect to other universes or just far parts of ours. Still, the math allows it. And where math leads, technology sometimes follows. 2. The simulation exit. If our universe is a simulation, as some theorists and philosophers suggest, then perhaps there's an outside. Just like a video game exists within a computer, maybe our reality is rendered by a system far beyond our comprehension. Could consciousness log out? Could we detect the boundaries of the simulation? Some physicists have speculated that patterns in cosmic radiation or physical constants might hint at coded behavior. Others believe quantum mechanics, especially wave function collapse, might be tied to information processing. But even if true, how would we leave? Would death be an exit? Would enlightenment be a key? Or would escaping the simulation require us to build our own, creating nested universes until we reach the source? Again, we don't know. But if we're inside something, maybe something is outside us. 3. Dimensional ascension. We live in a universe with 3 dimensions of space and 1 of time. But some theories, including string theory, suggest there may be 10 or even 11 dimensions. Most are compactified, curled up so small we can't perceive them. But what if we could reach them? What if there were a direction we haven't yet imagined? A dimension perpendicular to all others, invisible and untouchable, but very real. To leave the universe might not mean traveling far. It might mean turning sideways, finding a hidden axis in reality itself. Some theoretical physics proposes brains, multidimensional surfaces on which our universe rests. Others might lie just millimeters away, unreachable by light, but not by gravity. Could we tunnel into those realms? Send a signal? Step through? It's speculative, wild, beautiful, but not ruled out by science. And that's enough to keep asking. 4. Consciousness expansion. Perhaps the key to escaping the universe isn't technological or spatial. Perhaps it's internal. Throughout history, mystics, monks, and seekers have claimed to glimpse realities beyond this one through meditation, near-death experiences, or altered states of awareness. Are these simply brain phenomena? Or are they brief connections to something beyond? Some thinkers believe consciousness is not confined to the brain, that it may extend into the fabric of the universe itself. If so, could enlightenment or death offer passage to another layer of being? Not an escape through space, but a transcendence of form? We don't know. But the idea that the self can reach beyond the physical and beyond the universe is older than science itself. So, can we escape? The truth is, we don't know if escape is even possible, or if the universe is everything that can exist. Maybe there is no outside. Maybe the universe isn't a place, but a totality. Or maybe we're just too early, too young, too primitive. Perhaps in 1 billion years, minds greater than ours will find the keys to the next reality, to the multiverse, the hidden dimensions, or the truth behind the simulation. Or perhaps they'll learn that escape was never the goal. That understanding, not fleeing, was the point. That to know the universe fully is the only way to reach what's beyond it. And maybe, just maybe, the only thing capable of escaping the universe is the universe itself. Through us, through thought, through creation, through curiosity. Because even asking this question, can we escape the universe, is already a kind of freedom. The freedom to imagine, to reach, to dream beyond the stars. So tonight, as you fall asleep beneath the sky, ask not how far we can go, but how deep we can see. Because even if we never leave this universe, our minds already have. You touch the table. You feel the solid wood beneath your hand. You believe it's real because your senses confirm it. But what if they're wrong? What if matter, the stuff we think builds our world, isn't real in the way we imagine? Tonight on Infinity Beyond, we dive into one of the most disorienting and thrilling questions in science and philosophy. Is matter real, or is it just an illusion? Let's begin with the basics. Matter, in classical terms, is stuff, atoms, molecules, mass, things with solidity and structure. But the deeper we look, the stranger it gets. Atoms, which we once thought were tiny solid spheres, are mostly empty space. In fact, over 99.999% of the volume of an atom is void, nothing at all. The nucleus is tiny. The electrons don't orbit like planets. They exist in probability clouds. And when we go deeper, into quarks, gluons, and the quantum fields that underlie them, we find something unsettling. There's no thing there. Particles aren't little marbles. They're excitation patterns in invisible fields, waves of probability, fluctuations, ripples in an ocean we can't see. Even the concept of a particle might be just a convenient illusion, a way for our minds to make sense of a deeper, weirder layer of reality. And that's just the beginning. Quantum mechanics tells us that particles don't have definite properties until measured. An electron doesn't have a specific position or momentum until we ask the universe about it. Before measurement, it exists in superposition, all possible states at once. It's not that we don't know where it is, it's that it doesn't have a location. Reality, it seems, isn't made of things, but interactions, possibilities, information. Some physicists now believe that information is more fundamental than matter, that the universe is built not from particles, but from bits, zeros, and ones, like a cosmic computer. This is known as digital physics, the idea that reality is fundamentally computable, that space and time themselves might be discrete, like pixels in a game. Under this view, the table you're touching is not real. It's a rendering, not by a machine, but by the laws of physics. Your hand doesn't touch the table. It's repelled by electromagnetic fields. No atoms ever truly connect. And the hardness you feel? Just the result of forces, energy, not substance. So, what is substance? What is real? We don't know. Some philosophers like George Berkeley argued that matter doesn't exist independently of perception, that the only things that exist are minds and the ideas within them. This is idealism, the belief that reality is mental, not material. Modern science doesn't fully embrace that, but it can't disprove it either. In fact, some physicists, like John Wheeler, suggest that observer and information are the real building blocks of the universe. He coined the phrase, "it from bit," that everything, space, time, particles, emerges from acts of observation. That consciousness is not a byproduct of matter, but matter is a byproduct of consciousness interacting with information. If true, it flips our view of the universe, from a machine to a mindscape. So, what does all this mean? Does it mean that nothing is real? Not exactly. It means that realness might not be what we think. That what feels solid, permanent, and obvious might be just an interface, like a computer desktop. We drag icons, click folders, see images, but none of that is real in itself. It's a simplified layer hiding the messy code beneath. Perhaps matter, the world of objects and weight and form, is just a user interface for interacting with deeper, abstract layers of reality. Physics is trying to reach beyond the desktop, to understand the code beneath it all. Quantum field theory, string theory, loop quantum gravity. These are all attempts to describe what exists, and if anything does, beneath the illusion. And some go even further. They say that space and time themselves are emergent, that the universe is built not from stuff, but from relations, from patterns, from mathematics. Think about that. What if math is more real than matter? What if the universe is not a place, but a pattern? And what if we, as conscious beings, are the pattern becoming aware of it? It's disorienting, but also inspiring. Because if matter is not real in the way we thought, then perhaps reality is richer than we imagined. Not less. More flexible, more layered, more like a dream than a machine. And maybe that's the point. We're not trapped in illusion. We're surfing its surface, using perception to navigate an infinitely complex world built not from particles, but from meaning. So tonight, when you hold something, a stone, a cup, a hand, ask, is this real? Or is real just another word for what we can't explain? Maybe we'll never know, but the question? It's solid. It's here, and maybe that's enough. Numbers, patterns, equations, they appear everywhere, from the spiral of a galaxy to the veins of a leaf, from the rhythm of a heartbeat to the orbits of planets. But is this simply a tool we use to describe reality? Or is reality itself made of mathematics? Tonight on Infinity Beyond, we venture into one of the most fascinating and mind-expanding ideas in science and philosophy. Is the universe mathematical? Let's begin with what we observe. From the smallest quarks to the largest clusters of galaxies, math works. It predicts eclipses. It explains quantum mechanics. It models black holes, supernovae, DNA, weather, music, and motion. We build satellites using equations. We land rovers on Mars by calculating trajectories. We create simulations of the early universe by solving partial differential equations on supercomputers. But here's the mystery. Why does math work so well? Why should abstract symbols scribbled by humans, things like P, E, or 2, map so perfectly onto the behavior of matter, energy, and space? This question was asked famously by physicist Eugene Wigner in a paper titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It's not just that math is useful, it's uncannily accurate. So accurate that some scientists now believe it's not just a tool to describe the universe. It is the universe. The mathematical universe. Hypothesis physicist Max Tegmark proposed a radical idea. The universe is a mathematical structure, not just governed by math, not just described by it, but made of it. In this view, every particle, every law, every physical constant is not something embedded in a space that math describes. It is math. Electrons don't behave according to equations. They are equations. Space is not a stage where things happen. It's a geometrical structure defined by mathematical relationships. We don't live in a universe that obeys math. We live inside math itself. This means that if you could strip away all perception, all sensation, all metaphor, what you'd be left with is pure form, pure pattern, pure structure. And that structure is mathematics. Evidence in patterns. Golden ratios in sunflower seeds, Fibonacci spirals in shells, fractal geometry in ferns, lungs, river systems, lightning bolts, symmetry in crystals, waves in quantum mechanics, the curvature of space-time. Math isn't just in textbooks, it's in everything, in you. Your heart beats in rhythm. Your neural networks fire with logic. Your DNA encodes information using base pairs and probability. Even emotions, complex as they are, can be mapped to neurochemical feedback loops and bioelectrical signals. It's math wrapped in mystery. But is math discovered or invented? This is a question that splits thinkers into two camps. Platonists believe math is real, eternal, and discovered. The number pi existed long before humans noticed circles. The Pythagorean theorem was true in the geometry of the cosmos, long before it was scratched into sand. Nominalists believe math is a human invention, a language we devised to make sense of a chaotic universe. Useful, but not fundamental. Which is it? Well, if math is invented, why does the universe play along? Why does gravity follow inverse square laws? Why does light have a constant speed? Why are the laws of nature expressible in equations at all? And if math is discovered, where does it exist? Outside time? Outside space? In some eternal realm of form? If so, then what does that say about reality? Maybe physical reality is just a shadow, a lower dimensional projection of a higher mathematical truth, a code we're slowly decoding, the simulation parallel. This ties beautifully into the simulation hypothesis. After all, simulations are built entirely on mathematics. Everything in a game world, terrain, lighting, physics, is math rendered by processing power. If our universe is a simulation, then it must be written in math. Equations functioning as rules, logic loops governing cause and effect. So maybe the question isn't whether the universe is math. Maybe the better question is, what kind of math is it? What's the base language? What's the syntax of space-time? What's the source code of reality? We haven't found it yet, but theories like string theory, loop quantum gravity, and quantum geometry are all attempts to write the final equation, a theory of everything that reduces the cosmos to a single elegant framework. So, why does it matter? Because if the universe is math, then everything we experience, light, color, love, music, is the emergent result of a deeper structure. It means beauty has a logic, wonder has a pattern, and your mind, your thoughts, are the result of mathematics becoming conscious of itself. It means that beneath every breath, every heartbeat, every dream, there is order. Not the order of rigid rules, but of harmony, of symmetry, of infinite unfolding complexity. So tonight, when you look up at the stars, don't just see lights in the sky. See equations. See patterns older than time. See the great algorithm unfolding. And know that you are part of it. A fleeting variable, a dancing function, a beautiful expression in the formula of forever. You're here, breathing, thinking, feeling. But why? And how likely is that, really? Tonight on Infinity Beyond, we explore a question that blends biology, cosmology, and philosophy. Is life a cosmic accident? Or is it woven into the very fabric of the universe? Look around. Life is everywhere, on Earth. From the deepest ocean trenches to arid deserts, from volcanic vents to icy caves, life finds a way. Bacteria cling to rocks in radioactive waste. Organisms survive in boiling acid. Seeds sleep for centuries before sprouting at the whisper of water. Life, it seems, is tenacious, but is it inevitable? Or are we the result of a 1 in a trillion dice roll? Let's rewind. The universe began as pure energy, simple, hot, uniform. As it expanded and cooled, matter formed. Hydrogen, helium. Then, in the hearts of stars, heavier elements, carbon, oxygen, nitrogen, the ingredients of life. These atoms were scattered across space by supernovae, exploding stars that seeded the cosmos with potential. Then gravity pulled matter into clouds, clouds into stars, stars into planets. On at least one of those planets, Earth, chemistry turned to biology. But was that leap guaranteed? 1. The rare Earth hypothesis. Some scientists believe that life, especially intelligent life, is extraordinarily rare. That Earth is a lucky convergence of dozens of precise conditions. A stable star, a magnetic field to block radiation, plate tectonics to regulate climate, a large moon to stabilize rotation, water in liquid form, a relatively calm galactic neighborhood. Change any one of these, and life might never emerge. Under this view, Earth isn't just rare. It's unique, a biological miracle floating in a vast empty sea. But there's another view. 2. Life as a cosmic tendency. Maybe life doesn't need Earth's precise conditions. Maybe life is adaptive, not to specific environments, but to available ones. Maybe biology isn't fragile. Maybe it's inevitable wherever conditions allow complexity. After all, chemistry is universal. Carbon exists throughout the galaxy. Water is abundant. Organic molecules, the building blocks of life, have been found on asteroids, comets, and even in interstellar gas clouds. Amino acids have been detected in meteorites. This suggests life's ingredients are not rare. They are cosmic, and where ingredients persist, recipes eventually follow. 3. The principle of mediocrity. In science, there's a principle called the Copernican principle, or the principle of mediocrity. It states, we should assume we're not special, that Earth is not the center, that humanity is not unique. If life happened here, and the universe is vast beyond comprehension, then logic suggests it has happened elsewhere too. There are 2 trillion galaxies, each with billions of stars, each star with potential planets. There may be more planets than grains of sand on Earth. If even a fraction of them host habitable conditions, then life is likely common. Even if most life is microbial, even if intelligence is rare, there could still be millions of civilizations scattered across the cosmos. But if so, where are they? 4. The Fermi paradox. This is the heart of the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the silence of the skies. We've searched, we've listened, but so far, nothing. No signals, no artifacts, no signs of intelligent activity. So what gives? Maybe life is common, but intelligence is rare. Or maybe intelligence is common, but survival is rare. Civilizations may bloom and then burn out. Through war, environmental collapse, cosmic disasters. Maybe the great filter lies ahead of us. A wall few make it past. Or perhaps we're simply too early. The universe is still young. Stars will shine for trillions of years. Maybe intelligence is just getting started, and we're one of the first voices in a conversation that will echo through eternity. 5. The anthropic reflection. There's another explanation, more unsettling, that the universe seems fine-tuned for life because we're here to notice it. If it weren't, we wouldn't be asking. This is the anthropic principle. It doesn't say the universe was designed for us. It says, out of all the possible universes, we exist in the one that allows us to exist. Because in all the others, no one's there to ask. It's logically sound, but emotionally hollow. Because it gives us no insight into why life exists, only that it does. So, is life inevitable? We don't know. But the universe has evolved from simplicity to complexity, from quarks to atoms, from atoms to molecules, from molecules to cells, from cells to minds. That arc may not be accidental. It may be embedded in the very rules of physics, like a river seeking deeper channels, like light following geodesics through curved space. Maybe life is not the exception to the universe. Maybe it is the expression of the universe. The cosmos made conscious, matter that looks back, stars that think, galaxies dreaming of themselves. We've traveled far, through galaxies and black holes, through time, space, and thought. We've asked what the universe is made of, and what we are made of. But now we arrive at the question that echoes deepest. Do we matter? In a universe 13.8 billion years old, 93 billion light-years across, filled with trillions of stars. Do we matter? From a purely physical standpoint, we are small, tiny. The entire history of humanity, every war, every love story, every whisper, every breath, has taken place on a pale blue dot, orbiting a mediocre star in the outskirts of an unremarkable galaxy. And in the distant future, even Earth itself will be gone, swallowed by the sun, forgotten by time, cosmic dust. So it's tempting to say no, to believe we're insignificant, that we're just complex arrangements of atoms with illusions of meaning. But that's not the whole story, because meaning isn't measured in mass. It's not about size, or duration, or scale. It's about awareness. 1. The universe without us is silent. Without life, the universe simply is. It expands, it glows, it spins, but it does not know, it does not ask, it does not wonder. With us, even just for a moment, the universe becomes aware of itself. We are the cosmos reflecting. Stars do not write poetry. Quasars do not love. Black holes do not cry for the dead. But we do. And maybe, just maybe, that matters. 2. From dust to consciousness. The atoms in your body were forged in the cores of ancient stars. You are not separate from the universe. You are its expression, born not outside of it, but within it. Through billions of years of evolution, complexity, chance, and curiosity, the universe learned to think, to feel, to care. You are that. We are that. Not apart from nature, but its most recent breath. We are the voice of the universe, the part that says, I am here. 3. The power of choice. Unlike the stars, we have agency. We can build, destroy, create beauty or chaos. We write symphonies, paint dreams, imagine futures. We can choose kindness over cruelty, hope over despair. We can reach for meaning in a cold and indifferent cosmos and find it anyway. That is not small. That is staggeringly significant. Because in a universe where so much is dictated by gravity and chance, choice is a kind of miracle. 4. Perspective creates purpose. Yes, the universe is vast, but perhaps our smallness gives us clarity. If we are temporary, then every moment is precious. If life is rare, then every life is sacred. If nothing lasts, then what we build, love, knowledge, stories, becomes even more meaningful. We give meaning because there is no guarantee it will last. We build temples in the sand and know the tide will come. And still we build. That is purpose. 5. The cosmic mirror. When we look out into space, we often forget that we're looking into a mirror. The stars do not know we're watching, but we do. And that act of observation, of wondering, of caring, turns stardust into soul. We give the universe voice, color, emotion. In us, it dreams of itself. In us, it asks, what am I? Why am I? And though the answers may be incomplete, the question itself is beautiful. And it is ours. So, do we matter? The universe will not thank us. It will not remember us. But that doesn't mean we don't matter. We matter to each other, to the child born tomorrow, to the story still being told, to the questions yet to be asked. And maybe, just maybe, that's enough. To live with wonder, to die with grace, to look up at the night sky and whisper, I was here, I wondered, and in the end, I loved.